Today we are discussing about finite difference approximation to derivatives. Finite difference approximation is used to find the partial solution of partial differential equations numerically. Suppose we consider a function with two independent variables, that is u is equal to u of xy. U is dependent and x and y are independent variables. We can we know that ux and uy, uxs and uxy, uyy are given below. These are the partial derivatives of first and second order. So normally the x and y axis can be divided into rectangles of size x is equal to delta h and y is equal to delta k. The possible drawing is given here, and by drawing a set of lines x is equal to ih and y is equal to jk, and I and j values varies from 0 to 1 to etc. So x and y axis can be divided like a mesh or grid like structure, but in finite difference form in this method is quite simple. Finite difference form consists of quite simple method. We need quite simple method because x and y there are two independent variables. In finite difference form we can represent it as a one variable, so we can represent two dimension in the name of one variable, that is coordinate u of xy. To write finite difference form, put x is equal to ih and y is equal to jk. So u of xy is equal to u of ih, u of jk, and u of ih and jk and uij. We can represent it as uij. Look here, we can see that the in finite difference form the representation is quite easier because the two variable can be represented in terms of I and j very easily. So the mesh or grid like structure is of finite difference form is shown in this figure, and you can see that the representation. In order to change to finite difference form, the partial derivatives also have to be changed to finite difference form. So dou square u by dou x square and dou square u by dou y square also has to be changed to ordinary forms. In order to change this, we use the Taylor series expansion. We know that f of x plus h is equal to f of x h plus h into f dash of x h square by 2 factorial f double dash of x h cube by 3 factorial f triple dash of x, and we can see the Taylor series expansion. By this method we change the ui plus 1j and ui plus 1j to a Taylor series expansion method, and we can simply change to dou square u by dou x square is equal to uxx, and dou cube by dou x cube u into u xxx like that, and we can put it as equation 1. By rearranging the equation 1, we get the following equation: ui plus 1j minus uij is equal to hux and the corresponding terms. But by dividing it by h, we get ui plus 1j minus uij by h is equal to ux plus uxx h plus by 2 factorial plus uxx h square by 3 factorial plus etc. and the following terms. So we have to here we see that after the ux term, the other terms are of h order, and we can higher terms, and we can simply write as other higher terms. So we can generally say that ux is equal to ui plus 1j minus uij by h plus other higher terms of h. So the equation 3 is called the finite difference form of the ordinary partial derivative of ux. So we can say that whether OH OH represents the remaining higher order terms of H and predominant in the higher order terms, so it can be written as error in finding Ux, which is dou u by dou x, and equation 3 can be considered as finite difference forward operator for Ux. Similarly, ui minus 1j is equal to uij minus hux, h square by 2 factor uxs minus h cube by 3 factor uxss plus etc., and it is called Taylor series expansion of ui minus 1j. Here we can say that you can see that ui plus 1j and ui minus 1j in the following figure. Similarly from equation 2 we seen above, ui minus 1j minus uij is equal to minus hux plus h square by 2 factor uxx minus h cube by 3 factor uxs plus etc. The first method is applied for this also, so we divide this equation by h also. By that we get the following equation, and it is called the backward difference operator, the finite difference backward difference operator for Ux, and it is given as above. And the OH consists of higher order terms of H. We put it as equation number 4. We see that this is the equation number 1, and this is equation number 2. Equation 1 minus 2 gives the another result of central difference operator, and ui plus 1j minus ui minus 1j is equal to 2uxx plus 2uxx h cube by 3 factorial plus etc. ux is equal to ui plus 1j minus ui minus 1j divided by 2h plus other higher order terms of h square. We can put it as equation number 5. Equation number 5 is the central finite difference operator for Ux. In order to get the uxx or dou square u by dou x square, the second derivative, partial derivative of u with respect to x, we follow this method. That is, equation 1 and 2 are added, and we get the uxs is equal to ui plus 1j minus 2uij minus ui minus 1j by h square plus either high order terms of h square. We can put it as equation number 6. Here we consider that the equations are of I plus 1, or the changes happens to x axis or x variable. So dou square or the derivatives of first order and second order derivatives of x only. So we have to consider the dou square u by dou y square, or and dou u by dou y and dou u by dou y in central difference form and backward difference form and forward difference form. Similarly, we have done in earlier steps. We get the results very quickly, and the following results are obtained when we put u I j plus 1 and u I j minus 1 and by Taylor series expansion. In these equations 5 and 6 are more convenient, since as the s square terms appear, error will be minimum. So central difference operator is more convenient. Similarly by the above method, we can write as ui is equal to, we can get ui is equal to ui j plus 1 minus uij by k plus other terms of k, and equation we can put it as equation 7. This is the finite difference form of forward operator, and the ui and backward operator is given by ui is equal to uij minus uij minus 1 by k, other terms of k, and the central difference operator uij plus 1 and uij minus 1 by 2k plus 2 other terms of k square. Equation number 9 and equation number 10 represents the finite difference operator for dou square u by dou y square, or uyy. we can see that the above equations are got by simply putting as u. Here we put ui plus 1j, and we can put it as uij plus 1. So uij plus h dou u by dou y s square by 2 factorial dou square u by dou y square and h cube by 3 factorial dou cube by dou y cube. Simply changing as dou uij plus 1. Similarly, uij minus 1, we can change the above equations at ui minus 1 j to uij minus 1 and uij minus h ui and s square by 2 factorial uyy and h cube by 3 factorial uyy plus etc. So by changing this, we get the following difference operators and in finite method. This is called finite difference approximation of derivatives. Simply we concluding with the ordinary differential equations. When we consider these ordinary differential equations, we get the y dash of x as y of x plus h minus yx by h. It is called forward difference operator, and forward, and y of x minus h by h is backward, and y of x plus h minus y of x minus h by 2h is a central difference operator in ordinary method. But in partial differential equations in finite difference method, we get the following results as ux and uy as the given below, and here above ux and j is considered as a constant, and uy x is considered as a constant, and for the forward approximation and backward approximation and central approximation are given below. We can summarize it as follows. So we also know that in ordinary differential equation y double dash of x is equal to y of x plus h minus 2yx y of x plus y of x minus h by h square. But in partial differential equations, we can write as ui plus 1 j minus 2 uij minus I minus 1 j by, here it is s square, and here it is k square. It is called finite difference. It is called the finite difference approximation of derivatives. We don't consider the error terms. So the finite difference approximation of derivatives we got the equations. So we have to simply calculate the standard 5-point formula for a equation. So we consider in order to get the standard 5-point formula, we consider as an example of Laplace equation. We know that del square u is equal to 0 is a Laplace equation, or del square t is equal to 0 is a Laplace equation. So the solution of the equation can be found by or the adjacent points. By adjacent points, the nearby points temperature also can be found by standard 5-point formula. So in order to mention standard 5-point formula, we use Laplace equation as an example. So now we find the finite difference analog of Laplace equation. Substitute equation number 6 and 10 in Laplace equation. This is equation number 6 and this is equation number 10. So when we substitute this into equation number 11, we get the our Laplace equation. We get the following results as follows, and we have to neglect the higher order terms of s square and k square, and the or errors are considered h is equal to k, and put h is equal to k. We can add this, and we get the solution of following, and it is called the standard 5-point formula. Equation 12 is called the standard 5-point formula. We can see that here 5 points are there: ui plus 1j, ui minus 1j, and uij minus 1, uij plus 1, uij. So by one point function or 1 point's temperature. In the case of Laplace equation, del square T is equal to 0 is a Laplace equation. We have to find the temperature or energy for a Laplace equation. We have to know 1 point temperature or 4 points temperature. We can find the other points temperature. So temperature or energy. So Laplace by or function or Laplace equation. So it is called the standard 5-point formula. Value of u at any point is the means of its values of 4 neighboring points. So the first equation told is called the standard 5-point formula. This is the finite difference analog of Laplace equation, and temperature of ijth point is uij is the average of temperature of 4 neighboring points, and equation is totally is approximation. Here we do not consider, it is called approximation. Equation totally is called approximation because we do not consider the error terms. Considering the error terms, we get another equation. So we have to consider this is the equation number 1. This is equation number 2. Equation number 1 and 2, we get the equation number 14 which is consists of error terms also. Similarly, we consider the I and the j terms also, or the equation. Another equation we get equation number 14 can be rearranged as in the k type of equation as uij plus 1 minus 2 uij minus 1 uyy k square by 2 by 4 factorial u 5yy by k raised to 4 plus other terms of h raised to 6. Higher order of h raised to 6 of and put h is equal to k, we get the equation number 15 as given below, and the k square times r becomes h square times k raised to 4 times r becomes h raised to 4 times etc. And adding equation number 14 and equation number 15, we get these equations. We know that uxx plus uyy is equal to 0 by equation number 11, because we are considering the Laplace equation, which is del u is equal to 0 and del square u is equal to 0, and uxx plus uyy becomes 0 by Laplace equation. So the equation can be rearranged as equation can be modified as given below, and we can put it as equation number 16. Here we say that u is derived, the derivative of u is considered as from uxxx, or fourth order derivative and fourth order derivative of u in x and y also. Consider the fourth order derivative of partial derivative of u in terms of x, and ux can be given or rewritten as uxs into uxss and uxx into minus uyy, because uxx plus uyy is equal to 0 by Laplace equation. So uxx can be rewritten as u minus uyy. So uxx and minus is equal to minus uxx yy. So u for y is equal to minus u yy xx. Equation number, we can put this as equation number 17. So let's see the equation. We can put the given results. Example in equation 17 into equation 16. We get equation number 16 becomes we get ui plus the dou square dou x square plus dou square u by dou y square plus dou square y by dou y square and dou square u by dou y square, because and the order is not necessary, so we can consider it as 2uxxyy. Changing it, we get uxxyy and other terms of h raised to 6. So minus h raised to 4 by 6 by uxxyy plus other terms of h raised to 6. So the standard 5-point formula is rewritten as on the other side by minus 1 by 6 h raised to 4 by uxs by other times of h raised to 6. We can put it as equation number 18, and equation number 18, here we see that equation number 8 number 12 are same formula. The only change is the only difference is equation number 12 we do not consider the higher order terms or errors. Equation number 18 we considered the errors also. So